Hi, this is part third of Geostatistical Analyst online tutorials, and in this part we will talk about the deterministic methods. So here is the brief introduction about what are the deterministic methods and how these methods are different from another methods. So let's see this geostatistical analyst toolset, and we'll click here and we'll open the geostatistical wizard. And in this wizard, you can see here there are three options. The first is deterministic methods, second geostatistical method, and third interpolation with barriers. So when you will see this deterministic method here, yeah, there are four subsections, and all these subsections use the mathematical functions to calculate the values at unknown locations. And this is based either on the degree of similarity or the degree of smoothing. So inverse distance weighting, here you can see that this is based on the degree of similarity, and this radial basis function, this is based on the smoothing, based on the smoothing. So here we will take one by one here, and when you will see the geostatistical methods here, so geostatistical method use both mathematical and statistical methods to predict values at all locations within region of interest, and to provide probabilistic estimates of the quality of the interpolation based on the spatial autocorrelation among the data points. And so this was about the geostatistical. And here the third one, interpolation with barriers. Sometimes what happens, and that maybe there are some linear or barriers like mountain or some rivers or some canals, so there may be a drastic change in the interpolation, so that barriers you can use for the interpolation. So in between deterministic method, geostatistical, the major difference is here deterministic methods use mathematical models, and the geostatistical use both. Major part in geostatistical is statistical functions, and also the mathematical functions. Here deterministic methods are shown as follows. The first, we will use inverse distance weighted, then radial basis functions, global polynomial interpolation, and local polynomial interpolation. And the fifth one, that is interpolation with barriers. It is also a kind of deterministic method. So we'll discuss one by one. So first we will talk about the inverse distance weighted, and this method of interpolation is deterministic method, and this is based on the first law of geography. What is that law? That everything is related to everything else, but near things are more related than the distant things. So this law was given by Waldo Tabler in 1970. So this interpolation is based on that law, means inverse distance weighted. As distance will increase, the weight of the point will decrease. So our software is open and we are ready for our practice. This is our data here, and this data is having different attributes. We will use this temperature data for our interpolation. So let's make the label here for the temperature. This is our temperature data, and I will zoom in some part of the data. So if we will select some area, it will give us the interpolation surface for some area. Okay, we'll do for this area only. We'll go for geostatistical wizard. Here we can say deterministic and geostatistical. We'll choose the inverse distance weighting first. So one thing which is important to know that IDW, that is the inverse distance weighting, is a quick deterministic interpolator, and that is the exact. Exact means what? When interpolation is done, this 25.14, this value will be the exact for this point. After interpolation, this value will not be changed. There are some methods which changes this value, but in inverse distance weighting, this value will not change. Let's proceed it. Here, this is our data, and we'll give the attribute, that is the data field, and in the attribute part I will give the temperature here. Then next, and now this is very important to know because all these points will affect our result. The first thing is the point, the power, sorry. What power makes? Power function is important because this power, as we have discussed before, that as the distance increases, weight decreases rapidly. So how much this weight will decrease? What will be the intensity of the decreasing of weight? It will depend on this power. We can change this power, but by default the power is 2. So in ArcGIS 10.5 is a very good function. We can optimize here the power value. The power value is optimized to minimize the error. So let's do it with 2 this time. So this is the general property. Then search neighborhood. Search neighborhood search neighborhood will give the here search neighborhood that means which are the points which will give more width, okay, in the search neighborhood. So this time this is standard here by default. How many neighbors you want that the neighbor should play its role in the interpolation method. So here by default it is 15, and as you can see here the weights 15 neighbors are given, but you can change also, you can minimize or maximize also. Suppose if you will do it 20, it will take 20 points, 20 surrounding points for the interpolation. Sorry, these are the 20 neighbors. So because around this there are 17 only, so let's do it 15. If points are dense, then it will take the 20 also. So okay, here I'm giving 15. So maximum is 15 and minimum is 10. Sector type is important because it allows to means if there is only one sector, it will not bother for different sectors, but if you are giving more sectors, so data will be chosen from different 4 sectors. So here by default is 1, let it be done. Maximum, and like if I do it if I minimize to, this is 18 this time, if I do it 0, you can see the change here, the shape will be changed here. So if it is equal, the this is the anisotropy factor, means anisotropy factor is what? This is the ratio of major to the minor semi-axis length. So here length is varying, so this factor is also varying from the 1. If I will do the same, like if both the points are same here like this, then it will be 1. Okay, so here you can see the predicted value. If I will click on any point, it will show us the predicted value, and here there are 11 neighbors. So the highest weight is given to the nearest neighbor, that is in red color. But if you will see another color, like this is close to green color, and these points are far away from our predicted values. So this is the part which we can use. So let's move on. Here there are something like you can change the size of the point, and here if you want to give surface, remove the surface, you can remove the surface, and you can zoom in and zoom out. You can make it average, means fit to layer full extent. Thereafter we will go to the next here, and we can see our result, and we can see here these are the points which were used for the interpolation. These are the measured values, and these are the predicted values. Okay, and so this is the error. So there are 32 samples. If you will count the selected points, 32 points will be there. And as per this model, this is the prediction errors. So the mean of all error will be is minus 0.19, and RMS root mean square is 1.4. So these values are important when you are doing any work, and if you have given this surface in that work, then it is must to give these values, that whatever model I have used is it's means the errors are like this. This is validation, the validation of your data, the validation of your model. So if the error is more, then you cannot say that this result is good or this result is acceptable. The RMS should be low. So if you want to give this result, you can copy all, and thereafter you can copy it to another place like this. This is the regression function. What is the additive value, what is the multiplying factor, and what is your value, then it will give you the regression function. Samples are 32, mean is this. So the important thing is here is these values, this result is very much dependent on the power function. Okay, another factors are also affecting this result, but the most important is the power function. So this time you can see there is the RMS is 1.44, but if you will optimize it, then this root mean square error may be less also. So let's see what will be there in optimization. Okay, the power has given 5.7. So when you will see, it has reduced something 1.3. So you can reduce it this time with 5 it is 3. If I will make it 2, then let's see, this is 1.4. So there is a little change. So thereafter you can, okay, when it is optimized, better to optimize it, then next, then you can finish. You can export your result also. When you will export, it will be exported in the form of the shapefile, or in the form of feature dataset. When you will save it, cross validation result, you can do it in shapefile also. Save it, yes, okay. Let's make it finished first. So this is the summary of your method. Okay, so this is the surface which you have got, and the good thing is that this surface is very dynamic. If you are not satisfied with this result, then again you can go to the property method, and thereafter you can change also. Suppose if you think that okay, this power is much, I should not give as much power, I should give it 2, then you can make it 2 also. And when you will make it next finish, then you know the interpolation will change. And another important thing is next. Okay, so as you can see that what we did is here we exported the cross validation result here. So let's see the cross validation result here. This is the result, and we can make it up. Yeah, so in this result, these are the measured value, predicted value, and these are the errors. So if you are interested to see where error is more, then you can see that these are the points. Generally, what happened if your neighborhood is having less points, like the outer, because this point in surrounding has less points, so the error is more here. You see, similarly, this point is also having less neighbors. This side, no neighbor. So the and here also this point is also having less neighbors. So the prediction error is more in this case. So what is advisable is you can do interpolation for larger area, and thereafter you can clip the area of your interest. Okay, so this is your surface which you have created, and the same thing is here. If you want to export your validation result, you can make export with the help of this also. Okay, so it will give you the same data like this here. So this was about the IDW, and now we will proceed to another method. Radial basic functions are also exact interpolations that create the smooth surfaces. So radial basis functions produced good results for gently varying attributes because predictions are exact. In short, we can call it RBF, radial basis functions. RBF can be locally sensitive to outliers. So we'll practice it. So here for RBF also I will use the same data which I have used for inverse distance weighting. And I have not removed this surface because it will help us to compare the difference in between IDW and RBF. So for RBF I have to go to Geo-statistical, then wizard, then I will take the radius basis functions, and here I will take the temperature. So RBF is also exact interpolation, and it is also quick deterministic interpolators. So the here from inverse distance weighting, if you compare RBF, so RBF is more flexible than IDW, and there are some parameters which we'll see in the next here. In IDW we were giving the power, here we are giving the kernel function, and kernel function are known for the smoothing, and these kernel functions you can change. They have kernel functions are 1 2 3 5 categories. Each category there are the details in the help section, you can study for more. And these are the kernel parameters which you can modify also to optimize your result. And there are some weights are given here. This search neighborhood section is the same as we have already talked in IDW part. And here when you will see the weight here, For smoothing, the closer values, the weight is more here. If you will compare it with IDW, when you will compare it with IDW, so if you will see the weight here 0.23, 0.20, but in case of RBF, the values which are nearer has more weight than the values which are far away. So this is for smoothing your result. One more difference in between IDW and RBF is if you will see IDW, so IDW model cannot predict the values above than maximum and lower than minimum. But in case of RBF model can predict the values even more than the values which you have in your data and even less than the values which you have in your data. So it's important one that where we can use the the RBF function. We can use RBF. It is very good to use to produce the smooth surfaces from a large number of data points. So when there is a need of smoothing, it is very good model. So this function produces good results for gently varying surfaces such as elevation. The techniques are inappropriate, not correct when large changes in the surface values occur within a short distance. When you suspect that the same data is prone to measurement error or uncertainty, it is not good to use. So let's proceed to the next. So here we can see that these are the measured values here. These are the predicted values. The expert is showing us the measured values, and here this is predicted values. Some of the values are really far away from the measured values. These values you can see in the validation part, and you can export it. Okay, save it. Yes. Finish it. So, okay. So as we can see here, some of the values were very far from the measured values. So which are the values where error is the highest? Maybe this. Okay, here I didn't select the data points, so it has taken the whole particular region. So which are the place? Okay, yeah. Here we can see that the error is the highest. It shows that measured is 18, predicted is 13. What is the reason? Why? Because the surrounding values are close to 33, 34, 32, 32, 33. So here the prediction is around 30 only. But when you will see the value which is given here, okay, this is prediction is 18 here. Still the prediction is 18 here. Why? Because this is the exact method of interpolation. Means the point values will not change. That is why it is exact. Otherwise, if it is changed, then it will, we can call it inexact. But as you will move away from this, the values will change. Means right from 18 towards to 33, the value will be changed here. So this was about the RBF, radial basic function, and this we can go to these properties and we can see the weight, and we can optimize also here. So before optimization, the RMS is 1.37. If we'll optimize it, we'll change it 1.37. No need to optimize. Okay. So this was all about the RBF and the kernel function. The kernel parameters are basically used for the smoothing, and rest things are the same to the IDW. So I will finish it here. Okay. In the next, we will talk about another method. So now we will talk about the polynomial interpolation. And this polynomial interpolation we can divide into two categories, global and local. So as name indicate, global and local. Local is more complicated than global because in global there is no local variation. I mean, local variation is not included. So the major difference now we are talking the interpolation from previous one is global as well as local polynomial interpolation is inexact. Means the values, the your own values, measured values, observed values will be compromised, and those values will be changed when this interpolation will be done. Now I will use the same data here. The data is given, and we can use the whole degree data for this interpolation and geostatistical analyst, then wizard, and here you can see local and global polynomial function. So first let's see the global polynomial interpolation. So global polynomial interpolation, it fits a smooth surface. Okay, so conceptually what we can say is, let's take a data and see the result. I will take the temperature only and we'll go to the next, and here you can see there are no much controls because it is global. Order of the polynomial is 1 and the predicted values are here. So it is highly unusual as you are moving from one direction to another, the values are increasing. There are some local variations, so that local variation has been excluded here. And conceptually, we can say that global polynomial interpolation is like a piece of paper and fitting it between the raised point. So that paper, fitting the paper means there may be, so here this order will work, order of polynomial. So actually, what is this order here? When there is a flat plane without any bend, that is a first order. You can see here, like it is like you have bend a paper. But if you allow for one bend, is a second order. Here you have not allowed. Means there is no bend. There is a slope without bend. But if you allow one bend, then you have to give second polynomial. Okay, here there is one bend in this data. If you have to give two bends, then you have to choose third order of polynomial. Here you can see there are maybe two bends. If you are interested for three bends, then you can make like this. Similarly, you have to see your result, and if it satisfy your need, then you can do this interpolation. You can see the error here. RMS, you can see 2.15 in case of exact interpolation methods. It was around 1 point something. Now it is 2.15. So, okay, and so this is the way we can go for global polynomial interpolation. We can go for next here, and maybe we can finish it, or we can export this validation result for our analysis and evaluation. We can make it finish, and we can make it okay. So this is the surface which you are getting here, and the question is when we should use this global polynomial interpolation. Actually, if we need to fit a surface to the sample points when the surface varies very slowly from region to region over area of interest, for example, like pollution over an industrial area. And another is examining or removing the effect of long range or global trends. In such circumstances, the technique is often referred to as a trend surface analysis. So uh, we can say that global polynomial interpolation creates a slowly varying surface using low order polynomials. So if we'll increase the order, it will give us more variation. So this is global. Now let's try the local polynomial. So the data will be the same here, and we will choose local polynomial. So this is also a quick interpolator that is smooth, okay, and it is also inexact. And in the local polynomial, what happens? This is more complicated. If you will go through it, then you can see there are more controls given here. In the general properties, the first control is here, exploratory trend. So what does it mean? If you are trend means local, how much local analysis you want. So if you are giving 100, it will explore more locality. Okay. If you are giving it as a 0, there will be no local impact, and it will be like a global. So as you are moving from 0 to 100, you are going more local side. So let's do it, maybe 100, and order of polynomial you can change if you are interested for more bands. Here the kernel function is exponential, another also, because this function is for smoothing, and this is a mathematical model which controls your which will control your means the interpolation. And here you can optimize the model also. If you will click your RM mean, the error will be minimized. So if you have to take the advanced properties, then if you are interested to control your advanced properties, then you have to make it true. Then it will be highlighted. And here you can see your maximum neighbors, how many maximum minimum. You can control all these points. And these points are more or less same as we have done there in IDW. So you can change the maximum neighbors, minimum neighbors. You can change the major axis and the minor axis like this. You can change the bandwidth of searching. Okay, here you see like this. We'll make it next now, and we can see, okay, this, RMS, it is down now 1.5. So local polynomial method is giving us less RMS, means it is better model. So the important thing is that local polynomial is giving us more controls, and its this error is also less. So when to use local polynomial interpolation? Okay, global, this global interpolation, polynomial interpolation is useful for creating smooth surfaces and identifying the long range trends in the data set. But in geography, what happens? A variable of interest usually has a short range variation also. So if you are interested in short range variation, then you have to go for local polynomial. Yeah. It's sensitive to its neighborhood distance. Okay, global polynomial is not sensitive to neighborhood, but local polynomial is, this interpolation is sensitive to the neighborhood distance. So the output result will be better than global. We can make it finish, and we can make it okay for this. So the difference here you can identify if we say that, let's see where the difference is more. Okay, this is the method here. Next, let's export the validation result. Okay, here we have got our validation result. Where the error is highest, this is the error which is highest here. These are the highest errors. So you can see here, these are the errors here, and the measured value is 33, but predicted is 14. This is local, so it has taken the surrounding values. That's why the error is more here. Okay, so why I'm calling it inexact? Let's see the, this is the point here. Okay, this is the rainfall here. 20, the actual is here, the actual is 25.65, and let's see what is the interpolated. 25.65, this is the prediction map. Okay, 25, so let's see where is the, yeah, 25.65. Yeah, 25.65. So this is, if you will see here, the result is not 25.65. It has been changed. A little variation is there, but it is inexact. It is not the exact. It is not the same as our original data. So this is the reason why it is called inexact. For more information, you can visit the help part, and it is well explained there. So now we will proceed to another method. Now we will discuss the interpolation with barriers. So we'll use the same data here, and this data is showing the temperature We'll go to the geostatistical wizard. Then this is the interpolation with barrier, and here what we need is the barrier feature, and this barrier feature we can create a barrier feature here. Suppose there is a data set, and in between these two means there is a barrier which is playing some important role, means and we can make some kind of barrier here, and we can give some name like barrier. Okay, yes, so we have got this barrier here. So means this barrier will act like a barrier in the interpolation process. There will be no break in the raster, but the values which will be included in the interpolation, suppose here the values, if interpolation is going on, then for this area these values will not be included. So let's go to wizard. Here we can give a barrier, and let's see the temperature. Next, as you can see that this is also a kernel function polynomial. We can change the model also here, and the output surface, maybe prediction and prediction error also, and yeah, for this we can see here, if you can see here, means for this point the values for interpolation are included on the right hand side only, like you can see, only right hand side. So similarly here also no value is taken from left hand side. So this is the way you can do interpolation with barriers. And next, here some extra fields are given. So here RMS is 1.4, mean is this. So in case if at your surface there is a river, there is a mountain, or some another linear feature which is affecting the the data characteristics, so you can use the barriers for the interpolation. So this was all about the deterministic methods of interpolation. In the next video we will discuss about geostatistical methods of interpolation, that is here. So thank you so much for watching this video. See you in the next video. Thank you very much.